Swayam Prabha. Digital India. Educated India.
Hello learners, I am Dr. Rekha Sharma, retired professor UGC Human Resource Development Center, Rashtrasant Tukaroji Maharaj, Nagpur University, Nagpur. In this video, we shall learn refining of oils. Now, objectives of this module are: after studying this module, the learners will be able to describe the rendering of animal fats, to describe the extraction of vegetable oils. They will be able to discuss the chemical method of refining oils. Students will be able to discuss the physical method of refining oils and enumerate the advantages and disadvantages of chemical and physical methods of refining oil. Now, oil and fats do not occur freely in nature. They occur in animal tissues and in the seeds and fruits from which they are isolated, refined and processed for specific use. Fats are extracted from animal tissues chiefly by rendering and from vegetables by pressing and solvent extraction. Now, rendering of animal fat. Fats are produced by a variety of processes, generally referred to as rendering. Fatty tissues from both beef and pork are composed of essentially three components, namely water, protein and fat. It is the purpose of any rendering system to obtain as complete separation as feasible of these materials. In most cases, the fatty tissues are cooked and the fat is released by temperature and cell rupture. In an alternative process, the temperature is kept low and the fat is released principally through mechanical rupture of the cells. Thus, the term rendering of fat is the thermal processing operation that breaks down the cellular structures to release triacylglycerols from animal byproducts and underutilized fish species. The fat can be obtained from any of the following three methods: A. Dry rendering, B. Wet rendering and C. Low temperature wet rendering. Dry renderer. The cracklings should be gritty, fibrous and non-slippery. It still contains a lot of fat, thus fat is removed to 5% in order to economize the labor and to increase the keeping quality of material. Removal of fat is done from cracklings inside the centrifugal expeller and fat settling tank. Long bones from settling tank are sent to the digester. Dried and nearly fat-free cracklings are ground to recover meat meal. A cyclone and sacking unit allows the direct filling of bags. Lard and almost all the inedible tallow are produced by dry rendering. Advantages are: yield is nearly 20% higher and saving on labor is there. Now, wet rendering. This is generally vertical type equipment in which steam directly comes in direct contact with raw material or charge. The material is cooked at 40 psi for 4 to 8 hours. After processing, the tankage or slush is allowed to settle for 2 hours. The greasy or fatty material which floats on top is removed first, followed by water and finally by tankage with digested meat and bones. The bones are sent to bone digester. The lard produced by the wet rendering process is prime steam lard. Advantages: recovery of fat is better. Now, bone digester. Long bones are crushed and processed in steam at 60 psi for 2 hours. The steam separates most of the protein and fat. After extractions of fat and gelatin, the digested bones are chalky and soft and can be easily grounded to bone meal, which has about 32.5% calcium and 15% phosphorus. Now, low temperature wet rendering. This system uses heating, separation and cooling on a continuous basis and is regarded as an ideal purpose. The process involves mincing of the material, melting by live steam injection at 90 degrees, continuous separation of solids from liquid fats in a decanter centrifuge, further heating, centrifugation to remove the fines and cooling in the plate heat exchanger to below solidification point. Now, extraction of vegetable oils. Pressing. In India, oil has been obtained by processing oil seeds in village ghanis made of pestle and mortar, driven by bullocks from time immemorial. Power ghanis are now replacing non-power units. About 20% of the total production of edible oil in the country is by the ghani sector. The predominance of this sector is because of the consumers' preferences for the natural flavor and taste in ghani praised oils. Vegetable oils are obtained by mechanical expelling or solvent extraction of oleaginous seeds, namely soybean, rapeseed, sunflower, etc., or oleaginous fruit like palm and olive. The modern method of oil extraction by pressing is by the use of high pressure expellers. In this process, the oil bearing material is cleaned, tempered and dehulled, crushed or flaked and then passed through the expeller when the oil separates out. De-oiled cake is a good cattle feed. About 80% of the oil in the country is produced by this method. Now, solvent extraction. Extraction of oil from expellers is not a very efficient method. Pressed cakes contain appreciable quantities of oil. Therefore, it is now common to extract oils by solvent extraction or by combination of pressure and solvent extraction. With materials containing a low percentage of oil, solvent extraction is the only practical method of removing oil. Various organic solvents could be used, but the most commonly employed solvent is hexane. Now, qualities of crude oil. After extraction of the oil, the solvent is removed from the oil. The residue after solvent extraction, that is the protein rich de-oiled meal, can be processed as edible flour. About 1/10 of the oil produced in the country is obtained from solvent extraction. Vegetable oils generally contain triglycerides, about 98 grams per 100 gram. Triesters resulted from a reaction between glycerol and fatty acids and other substances in a minority proportion. Some of them such as diglycerides, vitamins, phytosterols, tocopherols and polyphenols have important health benefits in humans and therefore they should not be removed during processing. Other compounds known for their negative effect on quality and stability of oils include free fatty acids, unsaponifiable matters, waxes, pigments, solid impurities, mainly fiber, oxidation products like peroxides, aldehydes, ketones, alcohols, and oxidized fatty acids. These compounds are not toxic, but their presence in oil is undesirable as they affect the stability and the sensorial acceptability of consumers. Indeed, these molecules can give a bad taste and smell and could affect the functional properties of the oil. This is a chart showing the components of crude oil. Like it contains triglycerides 98 to 99 grams per 100 gram, which contains fatty acid and glycerol, whereas minor compounds are 1 to 2 grams per 100 gram, and it includes natural components like phospholipids, glycolipids, unsaponifiable matter, waxes, pigments and carotenoids, tocopherols, phytosterols, hydrocarbons, and triterpenoids. Oxidation products are peroxides, oxidized fatty acids, aldehydes, and many more. And chemical pollutants like pesticides, heavy toxic metals, mineral oil, organic solvent, aflatoxins, PAH. Now, refining of vegetable oils and fats. Refining. The oil must be odorless and rather neutral in taste, limpid and colorless, and it must be free of contaminants. Treatment that eliminates undesirable and toxic components in crude oils is known as refining. Refining is practically mandatory for crude oils that cannot be consumed as virgin oils to provide a product with an attractive appearance, a neutral taste, and more resistance to oxidation. Now, these are the undesirable constituents in oil removed during refining. The components are free fatty acids, phosphatides or phospholipids, oxidation products, flavors, waxes and pigments, and metals like iron and copper, chemical pollutants, heavy metals, pesticides, PHS, mycotoxins, and dioxins. Now, disadvantages of refining. Although refining extends oil shelf life, it has several disadvantages. One of the main disadvantages is the loss of substances responsible for healthy, pharmaceutical properties and technological interest in the oils such as tocopherols, phospholipids, squalene, polyphenols and phytosterols. Another notable disadvantage of refining is the formation of undesirable compounds such as glycidyl ester, 3-MCPD esters, harmful trans fatty acids, and polymeric triacylglycerols. Now, refining process. Two main industrial technologies used for vegetable oils refining are chemical refining and physical refining. Chemical refining removes free fatty acids by soda neutralization. Physical refining eliminates undesirable compounds deacidification by distillation under a high vacuum with steam injection. Now, chemical refining of oil. Chemical refining is the traditional method used since ancient times. It can be used for all fats and oils even when they have been slightly degraded. Each step of refining process has specific functions for removing some undesirable compounds. Chemical refining follows 6 processes. They are: first, degumming with the goal of elimination of phospholipids and mucilaginous gums. Second, neutralization, which allows the elimination of free fatty acids, phospholipids, metals and chlorophylls. Third, washing and drying in order to eliminate residuals of soaps and water. Fourth, bleaching aims at eliminating pigments, peroxides and residuals of both fatty acids and salts. Fifth, dewaxing has a main objective removing the waxes in the case of oils rich in waxes. And sixth, the final stage of chemical refining is deodorizing, which allows the elimination of volatiles, carotenoids and free fatty acids. Degumming. It allows the elimination of gums or mucilage composed mainly of phospholipids from the crude oil as well as compounds such as carbohydrates, proteins and trace of metals. Phospholipids or phosphatides are naturally present in oils. These compounds are important biological intermediates in the growth and functioning of plant cells. Phosphatidylcholine, phosphatidylethanolamine, phosphatidylserine and phosphatidylinositol are the major types of phospholipids. In general, vegetable oils contain two types of phospholipids, hydratable and non-hydratable. These compounds can trap metallic ions, that is copper plus ion, and prevent their catalytic activity related to free radical production in crude oils. Moreover, the presence of these compounds in crude oils poses many problems for storage and processing. Phospholipids are often linked to heavy metals, which are catalysts in oxidation reactions and sometimes can act as pro-oxidants in vegetable oils. The incomplete removal of phosphorus-rich components during alkaline neutralization creates a series of subsequent refining difficulties, resulting in the formation of a dark color settling in during storage. Phosphorus-rich components during alkaline neutralization creates a series of subsequent refining difficulties, resulting in the formation of a dark color settling in during storage. Therefore, their elimination from crude oils is mandatory. Indeed, the degumming stage consists of eliminating all compounds susceptible to becoming insoluble through hydration. For example, phospholipids, glycolipids, proteins, etc. There are four types of degumming processes, namely water degumming, acid degumming, dry degumming and enzymatic degumming. Chemical refining generally starts with the degumming process. The conditioning prior to degumming consists of making the oil with a small quantity of acid such as phosphoric or citric acid to dissociate non-hydratable phospholipids. For some oils, the first degumming with water can be done beforehand to remove hydratable phospholipids. The gums recovered represent the raw lecithin. The dry degumming process is recommended for oils with a low phospholipid content. This technique uses a concentrated acid, phosphoric or citric, combined with bleaching earth 1 to 3 grams per 100 grams. The acid 0.05 to 1.2 grams per 100 gram is dispersed in oil at 80 degrees centigrade. This acid dissociates the non-hydratable phosphatides into phosphatidic acid and is eliminated by centrifugation. The remaining amount is further adsorbed through bleaching earth. Dry degumming was developed for palm palm kernel, and coconut type oils containing small amounts of phospholipids. This technique is carried out at 120 to 140 degrees centigrade under reduced pressure. Its main benefit is the lack of generation of aqueous effluents except water is used in the vacuum system. The latest process in degumming is enzymatic degumming, which offers many benefits. Enzymatic refining is a kind of biotechnological process in which a phospholipase, especially phospholipase C, converts non-hydratable phospholipids into lysophospholipids. These components are insoluble in oil and need to be removed by centrifugation. Enzymatic degumming is a relatively new technology that emerged in the past 20 years. The process was first reported in the 1990s by Röhm and Lurgi, referring to the Enzymax process project. The enzyme was used to hydrolyze non-hydratable phospholipids into their hydratable form. Now, neutralization. Free fatty acids content is expressed in grams per 100 grams of oleic acid, except for some oils such as palm oil, where it is reckoned in grams per 100 grams of palmitic acid, and coconut and palm kernel oil, where it is in grams per 100 grams of lauric acid. Acidity depends on the nature of the oil, which in turn depends upon its geographical origin, harvesting, seed crushing conditions, and storage duration. It ranges from a value below 0.7 to 10 grams per 100 grams for some especially degraded oils. Vegetable oils containing a high percentage of free fatty acids, like either by hydrolysis and or by oxidation, must be refined to be edible. The presence of these compounds in crude oils poses many problems for the storage and result in an undesirable color and odor in the final product. Free fatty acids influence the chemical quality and the organoleptic instability of oil. Many methods for fatty acids elimination have been developed to improve the value of degraded vegetable oils. Some include chemical refining with caustic soda neutralization and physical refining based on steam distillation. In chemical refining, the oil is treated with an alkali solution, caustic soda, that reacts with the free fatty acids present as per the following equation and converts them into soap stock. RCOOH plus NaOH is equal to RCOONA plus H2O. In addition, when the neutralization is not properly done, the caustic soda may not only neutralize the fatty acids, which is the desired aim, but it also attacks the neutral oil in the form of so-called parasitic saponification that also reduces the yield, especially when crude oil acidity is low. Therefore, the concentration and dosing rate of the caustic soda need to be calculated based on the FFA of the degummed oil for optimal neutralization. Triglycerides plus caustic soda is equal to soap plus glycerol. In terms of economic perspective, caustic soda neutralization can be applied to oils having a percentage of free fatty acids greater than 15 grams per 100 grams because the loss of neutral oil in soaps becomes very significant. Moreover, other compounds can be removed in this step. These are an excess of phosphoric acid, residual proteins, residual gums, carbohydrates, oxidation products from free fatty acids, traces of metals and pigments which facilitate bleaching and deodorization. Moreover, a part of some bioactive molecules in oil which can act as antioxidants like tocopherols and polyphenols are also removed. Formed soap is generally insoluble in oil, hence it can be easily separated mechanically from oil based on the difference in specific gravity between the soap and neutral oil. The separated oil is then washed with water to remove the soap, alkali solution and other impurities to make it ready for the decolorizing or deodorizing process. Soap stocks are quite alkaline, pH is approximately 10 to 11. They contain sodium soap and caustic soda, but also water, salt, sodium phosphates, gums, carried over neutral oil, coloring agents, oxidation byproducts and various contaminants. This residual is referred to as residual oleins, which are treated and valorized in a special unit. Soap stocks have multiple end uses. These include applications in lipochemistry as an alternative raw material for biodiesel production and as an ingredient in animal feed. Now, washing and drying. This operation eliminates alkaline substances present in the oil from coming out of the neutralization turbines like caustic soda and excess soap, as well as last metallic and phospholipids, traces and other impurities. The crude oil needs to be well prepared, otherwise sizable emulsions could take place and part of the soap may not be eliminated. Washing water should be as hot as possible, 85 to 90 degrees centigrade, and should represent 5 to 15% of treated oil depending on whether the operation is done in 1 or 2 stages. It is preferable to use softened water and washing water should be sampled regularly for a visual check for the quantity of fat carried away after natural decantation or even better after centrifugation. The oil free of gums, traces of soap stock and other impurities is pumped through a plate heat exchanger where it is heated by steam. It is then sent to the centrifugal mixture to be combined with water and further centrifuged in a centrifuge for water washing. After this treatment, water washed oil is dried with a vacuum dryer until the moisture level of the oil falls below 0.1%. This stage will be followed by bleaching. The moisture present in the water washed oil can rapidly clog the filters, especially in the presence of soap. Now, bleaching. The objective of bleaching or decolorizing is to reduce the levels of color pigments, carotenoids and chlorophylls. It also further removes residue traces of phosphatide, soap, phospholipid contaminants, lipid peroxidation products and other impurities. Finally, it indirectly impacts the deodorized oil color. To perform bleaching, adsorption bleaching clays, activated carbon, spatial silica or a combination of these are used. The bleaching earth is the most popular adsorbent for decolorization of oil and the most widely used adsorbent material by the oil industry. Bleaching clay is favored over other adsorbents such as silica-based and AC-activated carbon products due to its low cost and relatively high adsorption capacity. Indeed, bentonite is the most favored bleaching clay used in the oil industry. To obtain a high adsorption capacity in the bleaching of some oils, a mixture of activated carbon and bleaching earth is used in refining industries. In general, the amount of activated carbon must be in the range of 5 to 10 grams per 100 grams to the amount of bleaching earth. The amount of adsorbent used ranges between 0.1 and 3 grams per 100 grams depending on the crude oil quality. However, other high percentage bleaching materials can be used to meet final color requirements. The pre-treated oil is heated to 90 to 110 degrees centigrade under vacuum and afterward is mixed vigorously in the bleacher with the adsorbent, that is with bleaching earth and activated carbon. After a retention time of 20 to 40 minutes, the oil adsorbent mixture is filtered. Only filters in the separation of oil adsorbent were used because the centrifuges process is not suitable for this separation. Therefore, short filtration times, efficient filtration and minimization of oil retention on the adsorbent matter are necessary. After this filtration, the oil is now ready for the deodorizing process. Dewaxing or winterization. Waxes are esters of long chain primary alcohols and long fatty acids. These acids have low solubility in oils, are high melting and usually crystalline during the winter season at low and room temperature. The wax generally does not negatively affect the functionality of the vegetable oil. The presence of wax affects the quality aspect of the oil, which gives it a cloudy appearance, especially during the winter season. Its hazy appearance is due to the precipitation of dissolved waxes. The dewaxing process is called winterization. The term winterization appears as during winter when the temperature is low, waxes present in the oil crystallize, thereby giving a hazy appearance to the oil. This process concerns a few types of oils rich in waxes such as rice bran, canola, corn germ oil, sunflower and olive pomace. The dewaxing process includes three main processing steps. In the first one, the bleached oil should be heated to 55 degrees centigrade to make sure the oil is completely liquid. Secondly, the oil is cooled slowly to 10 to 15 degrees centigrade. Ideally, the chilled oil is held for several hours at its temperature. In the third step, after finishing the crystallization, the cooled oil is pumped into a filter machine to separate the wax from vegetable oil. The filtration yields a clear liquid oil and the byproduct waxes. Now, deodorization. A deodorized oil is devoid of any taste, even pleasant ones. Deodorization is a simple distillation process. This operation allows for the elimination of free fatty acids and removes odors, different of flavor components and contaminants, especially pesticides, light polycyclic aromatic hydrocarbons and other volatile components. Deodorization also removes residues of mineral oil saturated hydrocarbons, that is MOSH, and mineral oil aromatic hydrocarbons, that is MOAH. On the other hand, deodorization also has other negative effects. Among them, the important bioactive molecules such as tocopherols, squalene, sterols, and polyphenols may be removed in this step. The most important are the destruction of some essential nutrients, unwanted side reactions like cis-trans isomerization. Here, the double bond isomerizes from cis to trans, then conjugation and polymerization. Also, it sometimes generates other unwanted compounds such as 3-MCPD esters. This 3-MCPD esters has been identified as a new class of oil refining contaminants. Deodorization is a vacuum steam distillation. The process involves the passage of steam through layers of oil held in trays and heating to high temperatures 180 to 240 degrees centigrade using a high pressure steam boiler. Utilizing a very high vacuum between 2 and 8 mmHg, the process removes undesirable odors caused by aldehydes, ketones, alcohols, short chain fatty acids, and thermolabile pigments. It is a steam stripping of taste and odor conveying substances that are more volatile than oil. The obtained oil is subsequently conditioned under nitrogen to protect it from oxidation. Now, physical refining. The process consists of same steps described in chemical refining except for the alkali neutralization process. Chemical refining consists of removing free fatty acids by adding caustic soda and separating the soap by centrifugation, while physical refining in the last step removes free fatty acids and other compounds by steam distillation. This process is also known as steam refining. Physical refining of crude oils therefore overcomes the disadvantages of neutralization by sodium hydroxide. Indeed, this process, which is deemed to be eco-friendly, minimizes liquid effluent generation. Another advantage of this process over chemical refining is that it is more economical. For example, fewer chemicals used, lower investment cost, lesser energy input, and improved yield. However, this process is not suitable for all types of oils since it is hypersensitive to crude oil quality. Indeed, physical refining is used for oils with high acidity. Considering the phospholipids content, Dumont and Nerin proposed two physical refining processes depending on the phospholipid content in the crude oil. In general, physical refining includes the following three main processing steps. First, degumming to remove phosphatides. Second, bleaching and filtration to eliminate color pigment. And third, deodorization allows the elimination of free fatty acids and other volatile compounds. Now, dewaxing. Sometimes the dewaxing process is added for types of oils rich in waxes. For example, fatty acids with low solubility in oil and high melting esters of fatty alcohols such as corn, rice bran, canola and sunflower oils. The principle of physical refining includes the following three important steps. The first step consists of subjecting the oil to phosphoric acid in the short mix chemical refining process. For degumming, it is most important stage and must be performed carefully. Now, bleaching. Bleaching or decolorizing is the second step. The main aim of bleaching is to reduce the levels of some colored pigments, that is carotenoids and chlorophylls, but it also further removes residues of phosphatides traces phospholipids traces contaminants, lipid peroxidation products and other impurities. The oil is then mixed with acid activated bleaching earth or another adsorbent. The standard bleaching process temperature is 95 to 108 degrees centigrade. Spent adsorbent along with some precipitated carotenoid and other impurities are then removed by filtration. After this step, the oil is ready for deodorizing. Deodorizing, the final step in the physical refining of oils is deacidification and deodorization. The deodorization process has three main objectives: removal of volatile components such as free fatty acids, different off flavors and contaminants, that is pesticides, light polycyclic aromatic hydrocarbons, etc. However, it can eliminate partially some bioactive components like tocopherols, sterols, etc. The second objective is thermal bleaching of colored pigments and peroxides. And third objective is to obtain better quality, a more acceptable aspect and more flavor stability during its shelf life. The deodorization process is fully determined by four process parameters: the amount of stripping steam, time, pressure and temperature. Deodorization is usually carried out at high temperatures, that is above 200 degrees centigrade with low vacuum pressure. The use of high temperatures and vacuum often results in the formation of negative side products. Physical refining offers great several advantages over chemical refining for vegetable oils. Now, this table shows the advantages and disadvantages of chemical and physical refining. The advantages of physical refining are lower investment cost, fewer byproducts generated, less energy consumed, fewer chemicals used, environmental friendly, and next is improved yield oil. Whereas advantages of chemical refining are simple operating process and second, efficient process to eliminate free fatty acids. Disadvantages of physical refining are not suitable for all types of oils, second, requires high temperature and vacuum, and third, can form unwanted products. The disadvantages of chemical refining are production of side products, expensive process, removes a high percentage of oil, can form unwanted products. This is the general overview of the chemical and physical refining process of crude oil. Now, crude oil is obtained by solvent extraction or mechanical extraction. Then if it goes to chemical refining, the process is degumming, where phospholipids are removed, then neutralization, by which free fatty acids are removed, then this undergoes the pigments, where dewaxing is done, where pigments are removed, waxes are removed and distillated acids are removed. Whereas in physical refining, degumming is done, which undergoes bleaching, then dewaxing, deodorization, and finally refined oil is obtained. Now let us summarize. Oils and fats do not occur freely in nature. They occur in animal tissues and in the seeds and fruits from which they are isolated, refined and processed for specific use. Fats are extracted from animal tissues chiefly by rendering and from other sources by pressing and solvent extraction. In rendering process, fat from animal tissue is extracted by heat. Oil extracted by the above methods are crude and contain many other constituents like free fatty acids, unsaponifiable matter, gums, waxes, mucilaginous matter, a variety of coloring matter, metallic contaminants, undesirable odoriferous constituents, etc. Two main industrial technologies are used for vegetable oils refining, namely chemical refining and physical refining. Chemical refining removes free fatty acids by soda neutralization. Physical refining eliminates undesirable compounds by distillation under a high vacuum with steam injection. These are the references. With this, we have come to an end of lecture on refining of oils. Thank you.